Good morning, everybody. This is Sue Ewig, and we are so excited to have you on the line today. I'm joined by Chris Skrinek, who is our lead partner solution architect for machine learning and artificial intelligence for partners. This is going to be a great topic. You can see that the title recommendation engines using Object2Vec covering factorization machines as well. So I'm going to go ahead and let Chris get started. If you have questions, there is a question pane down here on the right nav of your GoToWebinar screen. Pop your questions in there. Chris will do his best to answer those questions during the webinar. And if not, we will email out a list of all questions if there are a whole bunch that we can't get to after we finish. So without further ado, Chris, why don't you take it away?
All right. So good morning, everybody, or good evening, wherever you are in the world. As Sue mentioned, my name is Chris Skrinek, and I am the Global Machine Learning Segment Lead, Partner Solutions Architect. So recommendation engines is really a phenomenal topic for us at Amazon. We're known for them, of course. And what I like about this particular presentation is the narrative. If you've been doing data science and machine learning for a while, you know it's not a straight line. I'm actually going to walk you through some of the journey that we took to get to where we are today with recommendation engines at Amazon. So you're welcome to follow along with me. I have at the bottom there a little bit.ly URL for the notebooks that I'm going to be showing at the end of this particular presentation. But then starting at the top, we're going to talk about what is the problem. Excuse me. If you've been in any of my workshops, you'll know that I always start every machine learning problem with a clear identification of what the business problem is. We're going to do that here. We're going to take a look at a particular problem of expanding global opportunities for our vendors who sell on the Amazon retail site. We're going to take a look at sort of the origins of recommendation systems, and that involves a pretty simple math problem that we generally call matrix factorization. And then we're going to take a look at a new product that we offer as a SageMaker built-in, which is really the origin of this whole series, which we call Object2Vec, but we call it also AnyToVec, and you'll see why in a few moments. So that URL is going to go away if you want to follow along. It's bit.ly rec engine, and I'm going to move forward. So the business problem itself starts with expanding global opportunities for vendors on AWS. There's about 2 million sellers that sell on the Amazon, not AWS, but Amazon retail site. 300,000 of them we've identified as large sellers. There are even, the larger ones are selling in a limited marketplace, and only very few cross borders. So there are three main obstacles to sellers who want to go global. First of all, they don't know if there's demand. They don't know if they will actually be able to sell their products, if there's interest in their products across borders. So we want to be able to highlight to those using recommender systems, those that can and should sell abroad, right? So a little bit about machine learning at Amazon and how it's evolved in our retail business. First of all, we use machine learning just about anywhere, and we've been doing it for more than 20 years. It's very different. We have a number of very different systems, and many of those systems produce, well, our estimate is well over 100 billion predictions every single day. There are more than 2 billion products that are sold on the Amazon retail site and more than 2 million sellers. As mentioned, we have about 300,000 target sellers. So the real question is, how do you take this enormous matrix? If you think about the characteristics of just the target sellers, just that 300,000, and the billions of products and all the product features that they have, when we first look at this problem and how could we offer it to this group, we came up with a somewhat disappointing number. We were only really able to provide rich recommendation systems for 7,000 of those sellers. So why is that so low? Well, first of all, we may have been too ambitious in the output. So we began to take a look at this, and rather than doing monthly predicted forecasts, we for every product they're selling, we expanded that to annual projections. We reduced our data points. We originally reduced them down to 50K on our data points, but still there was not. The other problem that we had is we just didn't have enough data to really provide rich recommendation systems. Just generally, what's a good recommendation system? Well, if you're consistently putting bestseller products on a site, that's a very poor experience. It's hardly customized. So after a year of feature engineering and data aggregation, eventually we decided to, once again, get rid of the monthly granularity, provide only annual. So we have this famous flywheel that we use at Amazon, which really describes a lot of how we do what we do. And you could say it starts almost anywhere on this wheel, but if we start with selection, and then we take a look at the customer experience and we improve that, that drives traffic. Traffic brings more sellers. And as you can see, the implications of having more sellers and better customer experience means we can build more infrastructure and lower our prices, etc. So the question was, how do we move this flywheel now to a machine learning environment? And what are the elements of a machine learning flywheel that will drive a virtuous cycle? The principal output of machine learning is predictions. They're the basis of virtually every decision-making process. That's what makes machine learning special now, is that predictions have become cheaper, not necessarily cheap, but certainly more affordable than they used to be by factors. That improves the customer experience when they are making more informed decisions. That drives more traffic, which provides more data, which is the essential food for machine learning. So taking this flywheel into consideration, we looked at all of the elements that are required to design a good recommendation system at Amazon. First of all is ranking, product ranking. This is where most customers first encounter machine learning on Amazon. It's through the search engine. So search will first retrieve a set of what we call ASINs, Amazon, I don't know, product numbers, something like that, that are relevant to the search query. Then we rank them. We have a ranking algorithm where the relevance is based on textual similarity and popularity. Next then, we introduce the recommender system itself. Now, personalization, which is an important part of any recommendation system, essentially have two data sets. Who are your customers? What are the features of those customers? The other data set is the product. What are the features of those products? So that's the second part of that. Next is classification. So classification problems can be found throughout Amazon. Many problems can be reduced to a binary classification like fraud, spam, category mismatch, etc. But because binary classification only has two classes, there's still a continuous prediction problem that can be interpreted as a confidence in the prediction. Because we have billions of ASINs and more than half are sold by third-party vendors, they should be classified across multiple dimensions, such as color, category, size, etc. And while a human can classify them, in order to scale, we had to do something, right? We had to start introducing some automation. Next is considering regression. Now, regression, of course, is used to predict a continuous value, 0 to 1, 1 to whatever number is the maximum in your set. So you'll hear the term logistic regression quite a bit when talking about recommendation systems, but this is actually a classification algorithm and not really a regression algorithm. So let's talk about that. Clustering is an important technology in machine learning. It's where you're going to find the nearest or closest match to near duplicates. And when you think about the products, and you can see these jackets on the right, they're really similar. They look the same. They may be different sizes. They may be coming from different origins. They'll certainly have different prices. But being able to group near duplicate ASINs was a really important aspect of reducing the dimensionality of the problem that we're facing here, so that we could provide recommendation systems to a greater number of vendors. Last but not least is finding uncommon things. And this is a critical element in making your recommendations, making sure that they have a broad appeal. Amazon Fresh uses machine learning to detect the freshness in fruits. This is a good example of just doing a simple classification based on computer vision. We determine whether they pass or fail based on that visual inspection. And before Amazon Fresh was using machine learning, humans had to do this job. But scaling was difficult. So once again, just sort of emphasizing the value of modern machine learning in catching anomalies and what could be done in this area. So that's kind of an introduction to the problem set at AWS. Of course, Amazon uses machine learning in many other areas, including automation, drones, so all these various experiences. All right, so now let's get into the meat, which is common recommender systems using matrix factorization. So matrix factorization is a technique to recover or to really reduce the dimensionality of a problem set to create factors. It's famous for winning the Netflix prize. I think it was the $1 Million award. I forget what year it was. It's 5 or 6 years ago at this point now. But it's a real simple equation where you're taking these two data sets that I was talking about earlier, your user factors. So what are user factors? Well, that could be your geography, your age, previous buying history. It could even include things like click trail, whether you use mobile app. The user factors in a recommendation engine are feature engineered to be the most relevant to the way that you understand your customers. Personalization is a critical aspect of this, but there's really no small box that you could just kind of say, okay, these are going to be your user factors. For example, if you're in oil and gas, you want to categorize your customers. You might have a relatively small number of customers, but you want to make sure that you're always providing the most relevant information to those customers. That's going to be very different from media and entertainment, and different yet from online retail, which is what we're talking about with Amazon with this particular recommendation system. Now, we're going to use the Movie Lens data set. It's kind of the hello world of recommendation systems. And you'll see why in a moment. It's actually a really well-known data set. But think about movies for a moment, and what are the features of a movie? Well, there's the genre. Who are the stars in this movie? What's the plot? Is it dialogue heavy? Is it an action heavy movie? Is there CGI for interesting computer graphics, etc.? So the problem of putting together these two factors to create personalized recommendations. In other words, taking the features that you've determined are most relevant for your customers and taking the features that are most relevant for that product and put them together is really no more difficult than a simple matrix factorization. Now, what is a matrix factorization? There's a great little website here that is just called matrix multiplication .xyz, and I really like this example. So matrix multiplication is just a dot product of two matrices, and I love the way this is illustrated right here. You can actually just walk through and see you take one matrix, you multiply it then by each of the factors that are given by their array. The dimensionality of that array needs to be compatible, and then you have your output here. So when we're talking about a dot product or a matrix multiplication, we're not really talking about some kind of arcane math. It's just as simple as what you saw on the screen right there. All right, so this is basic matrix factorization. You take your movie factors, you take your user factors, put them together, and you get a prediction. Now, there's a lot of problems I haven't talked about. I will talk about them in a moment. But before I do, I want to talk about, okay, that's sort of where it all started. Where are we going now? Well, we're in the world now of deep learning and using deep neural networks to create infinitely nuanced functions that can give us frequently much better results. So on a very simple basis, you could take those same two data sets, create a very simple neural network with two fully connected layers, and come up with your predictions if your data set is small enough. Now, keep in mind, we have billions of products and millions of sellers. This was clearly not going to work for Amazon. So when we began to look at the problem, we would first take the matrix as a linear transformation and basically think about it in terms of how can we decompose this into other matrices. So when you look at it this way, it becomes a little bit more of a math problem, a little bit more like singular value decomposition. And there's a way to actually put these features together where you can start to do some optimizations. Now, one of the first problems that you're going to come up with is the way you're representing the data. Clearly, there are very few users on any website that actually create a review or actually rate or rank a product. And the products themselves may not have a lot of features that can be evaluated by the users. So you're going to have very sparse data sets. So singular value decomposition provides a way to factorize that matrix into singular vectors and singular values so that you can refactor these values in a way where you reduce the dimensionality. So now let's get to the narrative itself. So the first approach that we used was simply to consider fewer products. And that makes sense. Originally, we had, as I mentioned, 50,000 products. It was a good first cut, but we still wanted to do better. We still wanted to cover at least our 30,000 top sellers. So we reduced the number of products that we would cover that, and as you can see from the chart here, we ended up picking about 16,000 products, which covered about 98% of the purchases. So putting that in a fully connected layer, using the basic matrix multiplication that we referred to earlier, we came up with some values that were good, but not completely satisfying. Our next approach was to take those weights and put them in a convolutional layer. So in a convolutional neural network, obviously you're going to get a much more rich data set. This is clearly all labeled data. So we were able to take the factors that were more latent in our data set and reveal them through our decomposition. The next approach we took was to just simply use fewer connections. So on observation of the actual production of the model, we noticed that there were quite a few layers that were simply unused. They were relatively easy to identify through hyperparameter analysis, and we took them out. So we're getting good, but we're not quite there yet. The last and final step was to use an algorithm that's almost as old as I am, called the Bloom filter hash. So I love this little napkin drawing. It almost looks like it's on toilet paper, where you'll see if you Google Bloom filter hash, you'll see all kinds of mathematical explanations. The reality of this hash is it's very simple. If you were to take each of your discrete classifications and give them a particular value in a hash, you'll see if you take a look at dog and elephant, as you begin to populate that hash, they're going to be represented by a unique set of elements within that hash. But as this particular hash was populated, cat and monkey occupied the exact same elements in that hash. So it's a great trick if you, it's a great algorithm if you want to be able to use recommendations and you can afford to have duplicates or perhaps irrelevant recommendations in this sense. Now, if somebody's looking for a movie and they just type Bruce Willis, and all of his famous movies come up, Die Hard, etc., and maybe one comes up that's not at all related to Bruce Willis, I don't think you're going to lose any customers, right? So the Bloom filter hash is an excellent alternative for reducing the dimensionality of these particular problems. So the combination of all of those efforts, and this is over a period of years, brought us to the point now where we're providing recommendations for nearly everyone in our vendor network. Okay, so then we began to take a look at, well, how can we improve this? How can we take some of the elements of recommendation systems that we do well and add them to more modern technology? So you may be familiar with Word2Vec. It's a simple, well, very popular embedding algorithm, which is a necessary pre-production for any kind of natural language processing. These models are shallow. They're just two-layer neural networks. What they do is they take a large corpus of text and they will vectorize them, and then by scanning through a large corpus of text, you'll begin to find factors that are similar to each other. Now, there's a lot of approaches to this particular problem, but in general, the outcome is sort of given by this model in the center. So if you go through this large corpus and you take groups of words, you'll begin to see that words like Netherlands, France, Spain, Italy tend to be clustered together. Now, these are n-dimensional spaces, and we reduce them to 2D just so you can kind of get the concept here. But Word2Vec is a very common and necessary aspect of doing natural language processing. Well, the semantics of machine learning, and in particular, what can be done with Word2Vec can be transposed to other problems. So just as you can find the similarity between, say, country names, you can also find the similarity between various products. Those products may be retail products like we've talked about, or movies themselves, customers themselves. So when you're talking about representing products, we are looking, if you take a look at this chart here, on the X2 chart, you're looking at where in the embedding space are products like soaps most similar to each other. On the far right, you have cereals, etc. So without getting too deep into the math, and by the way, I mean, all you can really do in an hour is sort of whet the appetite. The follow-up for this presentation, I have a number of URLs that I can give you where you can really go into depth on this topic. But you could see that this clustering concept, or it's really a similarity rating of the products, can represent many other kinds of fields for study. So this is all the motivation for creating a SageMaker built-in algorithm called Object2Vec. As I mentioned, it is an embedding. It's an embedding of pairs of objects. So embeddings are important in feature engineering because it will convert highly dimensional vectors into a lower dimensional space. Now, we want to do this not only to simplify the problem, make it easier to think about, but clearly the computational requirements of your system can be taxing. I mean, it can go beyond the ability to solve your problem. So we want to reduce the computational aspects as well as make the problem easier and clearer to think about. And this is important. without reducing the amount of information that you're processing. So it does make it much easier to do machine learning on sparse vector inputs, and that's clearly what we have in these systems. It captures the semantics of the underlying data by placing those similar items closer together, and those that proximity can be measured. So Amazon's, the architecture of Object2Vec really consists of these main components. First of all, there's 2 input channels. These input channels take object pairs of the same or different types as inputs and pass them to independent customizable encoders. So these could be sequence pairs, token pairs, etc. Then we have 2 encoders. The encoders convert each object into a fixed length embedding vector. Then we have what we call a comparator that compares the embeddings in different ways and creates outputs or scores that correspond to the strength of the relationship between each of these objects. So an example of the output score could be 1, right? It's like 100%. It indicates that there's a very strong relationship between the pair. It's more likely to be something, something in between 1 and 0. So what are the use cases for Object2Vec? Well, clearly collaborative recommendation systems, as we're discussing right here, which we also call collaborative filtering. I think Amazon has a patent on it from something like 1996 or 98. For example, in retail, it just doesn't require any information about the items or users themselves. So this is a really powerful approach to multi-label classification. It's also used for sentence embedding. So now, I hope you enjoyed that narrative. I like the story because, like I said, whenever I do my recommendation workshops, I always start with the business problem. This is a significant problem that we dealt with at Amazon, and the story itself, I think, is really interesting and maybe heartening to folks who've taken months and years to get to a machine learning product that's producing excellent results. So at the top of the presentation, I pointed you to a URL where you can find these notebooks. This first notebook does matrix factorization using deep learning in the way that we described a little bit earlier. I'm not going to dwell on this too much, but I would be remiss to skip over matrix factorization because frequently the simplest answer is the best answer. And if you have small data sets, if you have a data set, so for example, in this data set, we're using a subset of the Movie Lens data set to do our matrix factorization. This could be the right tool. So even though we have really sophisticated tools and tools that make you look smart when you talk about them, sometimes the simpler is the better. And so, but unlike just say a straight up matrix multiplication, like I demonstrated on this particular page, here we are using deep matrix factorization, building a very simple, somewhat shallow neural network to create our recommendations. So the first step of every data problem is to look at your data. Now, even though Movie Lens is well known and there are a few groups out there that maintain it and keep it up to date, it's important to take a look at the data and understand what we're looking at. Well, seeing as how we're trying to match ratings and predict the ratings of unknown users, new users coming to the website, it's important to look at those ratings themselves. And we could see that most movies are rated relatively high, between 3 and 5, with a peak at 4. So then we need to take a look at our users. Here we're determining, okay, how many users are in the data set, how many have actually rated websites. I'm sorry, movies, excuse me. And let me just get to the meat here. So down below here, we create our very simple neural network. Now this looks identical to the slide earlier in the presentation here. If you're watching this on a recording, you could go back. But we simply have our inputs. we create an iterator because that's what's going to do the matrix multiplication. And then we create 3 fully connected layers with our output determined by a linear regressor. If you take a look at this last line here where we do the actual fit, we're only iterating 5 times. We're using an atom optimizer and a learning rate of 0.001. And I, of course, have already run this. I don't want to put you through the pain of waiting for this to run. And you can see using root mean square error, we get continually better results. And we may even have a satisfactory result at the end of this first iteration. But what we did on the next iteration is we went for the larger data set, actually took a look at a few more factors within the data. In this particular example, we took a look at genres, ran the same, almost the exact same architecture for the neural network, and came out with slightly better results. So there are some recommendations at the bottom of this notebook to dig in a little bit more deeply on this topic. But what I'd like to do is step right to lab 2, where we basically solve the exact same problem with Object2Vec. All right, so here's the notebook that was put together by my team about a month ago to demonstrate Object2Vec on the Movie Lens data set. So we've already reviewed this. Here's the basic architecture for how it works. In this particular example, we're using the 100K data set. Now this does require that you create a bucket in advance. So if you run this notebook, make sure you read the whole thing. You do have to create a bucket for your data and the output of your data, because in this particular notebook, we're going to create an end-to-end solution with a production endpoint in SageMaker. We're also using something here called JSON lines. So we do a pip install. We're going to plot our data. And just scroll down here a little bit. Here we're doing a curl to copy our data set to our ephemeral storage that's right in the notebook that comes with a SageMaker notebook. Then we're going to break our data into train, validation, and test set. Now, using SageMaker built-in algorithms, there's a couple of things sometimes we skip in these seminars. Let me just say very briefly, there's a lot of power in SageMaker. Number one, if you use the built-in algorithms and you provide a validation data set, the built-in algorithms will automatically use that validation data set to do hyperparameter optimization. If you're not familiar with hyperparameter optimization, hyperparameters are the output of fitting a neural network. They are something, I compare them to the compiled code. If you were writing in C++ or C# or Java and you create a compiled object, you would never dream of using a compiler without an optimization phase. Typically using the raw tools, you have to do those optimizations yourself. Using SageMaker, we make it very easy, in fact, even automatic when you use the built-in algorithms to get that same benefit. So we split up the data set. And we are going to do the same thing we did before here. We're plotting out how many movies were rated per user. We knew that was going to be sparse in the first case. Let's just move down a little bit. I want to get to the Object2Vec part. We do a couple baseline comparisons. You can take a look at this on your own later. And where are we here? Here we go. All right. So this is another key thing that I don't want to glance over. Whenever you're using SageMaker built-in algorithms, you're typically going to be using you're always going to be using a container that contains that algorithm. So this is how we actually get the algorithm image. These images are open source. You can run them in local mode. This is a really valuable aspect of using SageMaker. In fact, we are going to plan a session on where we're not covering the tools themselves, but all of these small elements, like how can you run SageMaker locally, say on a small data set with your own GPU on your laptop with your own IDE, but then when you're ready to train the entire data set, as we have to for Amazon, you can train in the cloud, use SageMaker and just say, hey, I need 100 machines with GPUs running this. That's really just a matter of specifying the hyperparameter that says I want 100 machines running this, right? So here's our hyperparameters that are specified below here. We have done a session in the series already on hyperparameter optimization, so I'd refer to you to check our library on that. Now to run the algorithm itself, we set up an estimator. We're going to use our P2 instances here, and here's the training instance count. It's given as 1. Well, that makes sense for this particular problem. It's a small problem, but as I mentioned, the difference between using 1 and 100 machines here is, you just change the value for your instance count. That's the real beauty and power and simplicity that SageMaker gives you. We set those, and then of course we do fit. I have already trained this model. Here you see the output. This is also found in your CloudWatch logs. So all of this information on your training data is preserved. It's there for you to see, not just in the notebook, but through the SageMaker Console. In fact, were you to go to the SageMaker Console, which I've done right now, let me make that a little bit bigger, and you go to training jobs, you'll see that here are all those statistics. In fact, once you've downloaded that data, you can actually go to the algorithms page here. You could create your own algorithm. But if you wanted to create a training job just based off of the data that you had downloaded, you can pull down here, go to Object2Vec, and everything that you just saw in that notebook could be done right here, right from the graphic user interface, all the hyperparameter settings, etc. So also one of the reasons I'm showing this is, this is a real great way to check what's the documentation look like for this. You might recall our learning rate was 0.001. So, you can just change that right here. What are all these other parameters and how do they affect it? Well, for that, I refer you to the documentation. But often I will simply just go to the graphic user interface to see what all the parameters are for my hyperparameters when I'm training this job. And a single click from the GUI will train that job. Now we have a trained model that trained successfully. Next, we need to create a model. Now, when you use the SageMaker API create model, what you're really doing here is taking the model artifacts and marrying them now to an object that can be deployed, and that's what we have in the very next command, in production. Once again, you have all the features that you expect from AWS in terms of auto scaling, the number of instances that run. Right here, it's very, very minimal. We're just setting up one instance. If we wanted 10, we'd say 10. And we're running on a CPU-only instance, M4 extra large. Actually, I usually tend to use the C5s now. I should always look to see what the most modern choices are for your deployments because they definitely change over time. But this one command, deploy, creates a production endpoint. I'm going to go to the console again, just very quickly take a look at our endpoints. Take a look at this endpoint. Oh, I deleted this one. All right, so that one's not in production at the moment, but before I ran this notebook, it was in production. So to call that, by the way, it's really important to delete endpoints you're not using because they can be costly. And that's why I did delete that after I ran the notebook. You'll see it's at the bottom of every one of our example notebooks. But to call prediction on this, we use the predict command. We get mean square error of 0.93. That's very, very good. We compare that to other libraries, and we see that we have a pretty good model. Now we're going to call this in production with a recommendation task. I'm going to kind of skip past this bit to the very, very end because we have a really nice reference to a end-to-end model. If you do the, I guess I have to type this over here. If you do the workshop the way it's specified at this URL, and I'll make this a little bit bigger, you're actually going to end up running this prediction from Lambda. Now, we're emphasizing much more now a lot of the other tools, not just basic the buttons and knobs in SageMaker, but how do you put this in production from your web app or mobile app? You're typically going to use something like API Gateway to set up your post, your HTTP post, to call this algorithm, and then within API Gateway, you're going to call Lambda. So what this notebook does is it walks you through that entire process, step by step, of actually creating the Lambda that then calls inference on your model that's in production. Now, this is the down and dirty, how do you create a recommendation system both with deep matrix factorization and with Object2Vec. We do have a new product that's soon to be in general release called Personalize. It's very likely that Personalize will do 90% of the work that you just saw in those notebooks for you. So before you set off on, as it was for Amazon, a multi-year journey to create a recommendation system, what maybe if you're using some of the tools that are available, say in the machine learning zoos, might be reduced to a couple weeks or months, take a look at Personalize, sign up for the preview, see what you can do with Personalize, because it may reduce your problem to a few hours. We do have a demo of an end-to-end demo of the exact same data set, which we'll take a quick look at here. And I'll just randomize the output here, move it down a little bit. But here we see the characteristics that were sent to the HTTP post. We have, well, the user ID is not significant input, but the age, 30-year-old female, occupation artist. Here we see the movies that were recommended for that particular profile. Let's click next. Here we have 21-year-old female, a lot of artists in this data set. There we go, 39-year-old male engineer. So the data set here is 10 years old, so you're not going to get movies from last year. Actually, judging on the output here, it's more than 10 years old. But the basic concept of having highly relevant ranked recommendations for the data input. I like this 40-year-old female librarian. You're going to get Fargo up there first. So you're definitely going to get highly customized output with, well, at least using Personalized, a managed service that can be refreshed with a CI/CD environment, perhaps even daily, depending on how what the cadence is of changes for your particular data set. So that is recommendation systems using matrix factorization and our Object2Vec built-in. So I'm going to take a look at the questions now and see what we've got. And I just have to expand this on my view here because they're really teensy tiny. In a few moments. There we go. Any plans on moving from Jupyter to Jupyter Labs on ML and AMI? Not sure what you mean by ML and AMI, but if you go to SageMaker now and I go to my notebook instances, you'll see that you certainly can open in Jupyter Labs. We have another workshop that describes just some of the basics of how to add Jupyter Lab extensions, which can be extremely useful when you're using Jupyter Labs. But Jupyter Labs is built right into SageMaker. SageMaker is an extremely cost-effective way to run a Jupyter notebook. We certainly have Jupyter Labs here, so it's not like that's missing. But the best thing about running any notebook in SageMaker is, first of all, you could choose your instance. I typically use, you can see here, M5 4x large or C5 4x large. I think it's 9 cents an hour. And when I'm done, I just stop it. So I just clicked stop on my notebook instance there. I'm not going to get charged for it anymore. So you bring it up, you pay a dime for an hour, you turn it off at the end of the day, and you're done. Those endpoints, as I mentioned, they can be costly. So those are production endpoints, and they're designed for global scale. So you want to be careful about that. But the notebook instances in SageMaker are super cheap. You should use them. Okay, next question up is how would we filter recommendations to ensure only movies not viewed by the user? That's a great question. So obviously, let me back up a little bit. I like to say that machine learning creates features, not solutions. So what do I mean by that? Machine learning's great. It is simply a new paradigm for coding. In 2 or 3 years, everybody's going to be doing it. You guys are on the cutting edge, so congrats. But at the end of the day, data writes your code, but it cannot do everything. Features are going to exist in every software engineering environment in a pipeline. When I say pipeline here, I mean that you may have multiple calls to multiple models. Some of the customers that I work with, being based in New York City, are hedge funds that have been doing deep learning, machine learning for a long time, and they have 3,000 to 4,000 models in production simultaneously. Now, are they expecting any of those individual models to do comprehensive risk reduction, to do stock selection, to do timing? Of course not. They're operating within an ecosystem of software that's using the machine learning features to do the particular jobs that they need for that task. Filtering out recommendations, that's just a matter of taking the output from Object2Vec in this particular call, checking to see which movies have already been viewed by your users, and deleting them from the selection score. From the selection GUI. Okay, how do we create inputs for Object2Vec? For Word2Vec, it's a one-hot encoding of the text in the corpus. What's the equivalent? That's, first of all, that's a great question. How do you use this software? I know this is pedantic, but the SageMaker documentation is actually really good. So if you just search for SageMaker documentation, it'll take you right to the website. If you're online with me right now, if you're listening and clicking and paying attention, search for SageMaker and then click right here. I'll make it big so everyone can see. Click on PDF. Download that PDF, put it on your phone. Here's the reality, and this has been the reality in machine learning from the very beginning. There are no standards. There's no standard input to any particular machine learning algorithm. Where did my documentation go? There it is. So you need to, RTFM, I mean, you need to read the docs. That's all there is to it. Each algorithm maker is going to have particular peculiarities to the way that they call their algorithms. You can see Object2Vec here is documented. It's on page 179. I'll just click on that. So here it has the I/O interface for Object2Vec, right? So I won't go through this right now because this is definitely something you need to take a look at and implement it. But yeah, but that's the short answer to that question. And this is not unique to Object2Vec. If you use scikit-learn, if you're using any of the MXNet, PyTorch, TensorFlow algorithms, they're all going to have unique I/O requirements. All right, go ahead and put some more questions in. I'm happy to and eager to put some more. And there is, I can't copy and paste. One of our attendees here has put a URL in here that I would love to copy to the, wanted to recommend. I'd love to put it out here, but I just can't access it. I would have to type it by hand. I apologize. I'll give you another minute here for questions. Let's see, some of the resources, David Ping and his team did an excellent Object2Vec blog. I'll bring that up. There we go. You know, we're really sort of, I mean, this is just another in the continuation, the continuing program we have at Amazon, where we take what we're doing for our own business and we fully expose it to our customers at AWS. This is relatively new. This particular blog post here was from just before reInvent, less than 3 months ago. So these are new algorithms. You're the first ones to do these deep dives on them. Eventually this video makes it to YouTube, but you know, it's really nice to get in here early and take a good look at some of these sample notebooks. I know that, I believe Julian Simon has a treatment of Object2Vec as well. All right, well, I'm not seeing any more questions, so I'm just gonna thank everyone deeply for attending today. My job, I don't know the answer to every question, but I am the segment lead. So if you have any follow-up questions, here's my email address. Please don't be shy. Reach out. I don't permit blockers from anyone who's in any of my workshops. I may not know the answer to everything immediately, but I'm part of more than 250 developers, architects, and data scientists that very likely will. So thank you once again for attending today.